All right, let's go ahead and get started. I just want to make sure, so the sound is good in the back. Sound is good in the back, and people on Zoom, is everything good? All right. So the plan for today, I posted a more or less summary or topic list of the things I want to cover on Ed. And so the way the logistics are going to work, I'm going to try to answer questions also during the review session. But of course, but I also want to be mindful of the time so that we can get through all of the topics that we want to cover. And yeah.
So Zoom meeting recorded?
Yes, I'm recording the Zoom right now. Do you see it being recorded also?
Yeah.
All right. Okay, good. And so the way some of the logistics are going to work, so of course, I'll try to answer questions during the review session as well. But on Ed, there is a mega thread for Q&A as well. So if you suddenly in the middle, there's something you're not sure how it works, you just want to take a picture and just ask on Ed. So Tuni is here and he's answering. Say hi, Tuni.
Hi.
So he's answering all these questions. So he's monitoring the Ed and also the Zoom chat. So if there are any questions that pop up in the Zoom chat, and also if there's just something you see and you're like, I'm not sure where this is from, I want to ask a question about it, you can just take a picture or just type your question on Ed. And so Tuni is monitoring both of those things, and he'll try to answer your questions in real time. Is the sound echoing, or is it just me? Or does it sound good for you guys back there? It's good. All right.
I got it.
Yeah. Oh, I posted it on both Ed posts, the one I posted yesterday for the review session details, and also on the one with the practice question. Right, and so the topics that I cover are more or less very, very closely tied to what is on the practice exam. And as Noah and Matt mentioned, the practice exam is a very close representative of what the real exam will be like. And so hopefully the topics that I covered today during the review session will also closely correlate with those on the exam. Right, so I'm going to, are there any questions about the logistics so far? Yeah.
So we're not actually going to go over practice exam questions, so right?
I'm not going to go over the questions from the practice exam, but I've basically looked at the practice exam, wrote out what are the relevant topics, and then I will give examples that are not on the practice exam. But I'll take examples from the practice questions that I posted on Ed. Any other questions about the logistics? All right. So I'm going to start with a little bit of review of propositional and predicate logic. And in math, or this really, even though it's a CS course, it's really a math about CS class. In math, we are concerned with the idea of truth and of falsehood. And so in order to speak formally about these things which are true or false, there's what is called a proposition, which is simply a statement which is either true or false. And in order to reason about propositions, we're going to develop the system called propositional logic, in which we can reason formally about these propositions which are true and false. In order to prove that something is true, so in order to justify that something is true, we give a proof. In order to show that something is false, we give a counterexample. And I'd like to make, when I talk about propositional logic, I'd like to make analogies to algebra. In propositional logic, we also have variables. These variables, let's say we have a variable P and a variable Q. These are variables. And so just like in algebra, we would use variables like X and Y, and those variables will represent numerical values, say like X equals 5, Y equals 7. In propositional logic, we also have variables P and Q in which we represent in which P and Q are representing of propositions. One thing to keep in mind is that a proposition is either true or false, and therefore a propositional variable like P or Q essentially is, because it's representing a proposition, it takes on a value of true or false. Therefore, if we have algebraic variables like X, Y, or N or something like that, which represent numerical values, it should become clear that because these are Boolean variables, while the algebraic ones, say X, Y, and N, are numerical ones, that these variables P and Q cannot really be interacting with algebraic ones. And by interacting, I mean, it wouldn't be valid to say something like P plus X, because in this case, you would have like true plus like 5. And so statements that look like this are essentially mathematically meaningless. Maybe this one isn't such a common error, but sometimes you might see something like P equals N, and neither is that a mathematically meaningful statement, because P here is a Boolean variable, and N here is essentially a numerical value. And I'll probably make this more clear as we go into later topics in the review session. In algebra, we have some operations in which we can combine the variables to make more complex expressions. For example, you can add two variables. You can do x plus y, x plus n, x divided by n, x times n, in order to make more complex expressions. Likewise, in propositional logic, given propositional variables p and q, we can use various operations to make more complex propositional expressions. And the way that those are defined are through a truth table. So we have and, we have or, we have implies, and we have if and only if. And to define these, I enumerate all possible values of p and q and give the output for p and q. So p and q is when both are true, otherwise false. P or q is when either is true, otherwise false. P implies q, so is defined as true, false, true, true. I'll come back to this later, and this true, false, false, true. By looking, this truth table is probably pretty intuitive to you, other than maybe the if and only if or the implies. But I want to, instead of dwelling on just the very the raw truth values which I've written on the board, I want to give a few implications for why this truth table is important in writing proofs. And let's look at P and Q. In order to, I'd like to call your attention a little bit to the proof tips sheet that I prepared, that I put at the end of my practice questions. And so I'm going to essentially explain sort of the intuition behind some of those rules that I've written there. So P and Q, in order to prove that P and Q is true, in order to justify that P and Q is true, we need to prove that P is true, and we have to prove that Q is true. In other words, to prove an and statement, we need to prove individually the two statements are true. If we only prove one of them is true, we're not guaranteed that P and Q is true. Suppose we only prove P is true, we could still have Q is false and have the whole aggregate expression to be false. Therefore, to prove an and statement, we need to prove that both of these are true. Conversely, to use an and statement, if we know that an and statement is true, if we know that P and Q is true, then we are guaranteed that P is true and Q is true. And therefore, if we know that an and statement is true, we can also use the individual propositions as quote unquote ammunition for things that we can derive or conclude or use in our proofs. I'm going to move on to P or Q. In order to prove that P or Q is true, it is sufficient only to prove that one of them is true. If we know that P is true, once we've proven P is true, we'll automatically get P or Q is true. Once we've proven Q is true, we automatically get P or Q is true. Except to use a statement that's P or Q, that's in the form of P or Q, it becomes more difficult to conclude the truth values of individual values P or individual values of Q, because if I just know P or Q is true, it could be any of these three lines, and therefore I cannot conclude that P is true, or I cannot conclude that Q is true, because it's possible I end up in this case where Q is false, or I end up in this case where P is false. And so therefore, in order to prove a P or Q statement, we have to use a proof by cases. In order to prove a P or Q statement, we use a proof by cases. And the proof by cases is we assume P, and then we try to get our conclusion. And we assume Q, we try to get our conclusion. So I apologize for not really writing too much on the blackboard, but so P or Q, so maybe I'll write it here. So P and Q, just to recap, to prove, we need to prove P and Q individually. To use, we can use either P or Q individually, or both. For P or Q, to prove, we only need to prove one of P or Q, except to use, oh, I'm sorry, to use right, to use P, I'll do prove first. So to prove P or Q. Oh wait. All right, ignore what like the last 3 sentences I said. To prove P or Q, it's only necessary if we can prove that P is always true, or we can prove that Q is always true. We can always get P or Q is true. So we can prove P or Q individually. And to use, if we know that P or Q is true, we need a proof by cases. We need to assume P and then get to your conclusion. Assume Q, get to your conclusion. And the intuition here is that essentially if I know P or Q is true, I don't know which one is true. And so I say, in the case, all I know is that one of the two, P or Q, one of the two is true. So I'm saying in the case that P is true, I end up at the conclusion I want. In the case that Q is true, I end up at the conclusion I want. So in effect, when you reach this point in the proof and you know that P or Q is true, you're saying I have a fork in the road. I don't know which one, P or Q, is true, but no matter which path I take, I will always end up at the same conclusion. And that's how we could use a statement that we know P or Q is true in order to prove a desired claim. For implies, P implies Q, it might be a little bit surprising, but I think if I can try to give you the intuition is that we're saying if P, then Q. So if we know P, we have to be guaranteed that Q is true. And so if P is false, we have already sort of like all bets are off. Because if P is false, the preconditions have not been satisfied. And so sort of the result of that can be anything, like Q can be true, Q can be false. And sort of P implies Q kind of essentially just doesn't really care what happens if P is false. If P is false, then this statement almost has no force at all, because this only rests on the assumption that we know that P is true. Therefore, to prove that P implies Q, is this still in frame on the Zoom? Okay, good. Yeah, okay. So in order to prove P implies Q, and I think this is a really important point, in order to prove an if statement, we want to assume P, and then conclude Q. And so most of the statements you will have to prove in this class will be of the form P implies Q. They'll involve some preconditions, and they will involve a conclusion. And what you want to do, once you see a statement that you have to prove P implies Q, you're going to assume P. Just write down assume whatever this P is, and then you write down at the end, you want to conclude whatever this Q is. If you know that P, so this is to prove. In order to use a statement of P implies Q, if you know P, then you can conclude Q. So if you previously already know that P is true and you know that P implies Q, then you can also know that Q is true. Finally, P if and only if Q. This is simply just P implies Q and Q implies P. Therefore, to prove it, you essentially just have to prove 2 if statements. To use it, if you know P, you're guaranteed Q, and if you know Q, you're guaranteed P. Any questions so far? All right.
You know P, you're guaranteed.
I'd like to give you a few sort of useful identities involving these logical operators, and as well as their negations, and ways in which we can perhaps convert between using ands and ors or using implies. One of these laws is called De Morgan's laws. It says that not of P and Q is equivalent to not P or not Q. And analogously, not of P or Q is equivalent to not P and not Q. This notion of moving the nots in and flipping the ands and ors or flipping some other thing, it will come up as a recurring theme. Another maybe useful identity or propositional identity is how to convert between, say, P implies Q and something involving only ands and ors.
Oh, that makes sense.
That's good. I'm very flattered by your affirmation. All right. So to convert P implies Q to a statement involving ands and ors, let's look at the truth table for P implies Q. P implies Q is true. So if I know P is false, I'm guaranteed that this is true. So if I know not P is true, guaranteed P implies Q is going to be true. If I know Q is true, I'm guaranteed P implies Q is going to be true. So how I'm converting this is I'm saying, I'm looking at this truth table and I'm saying, when do I get that P implies Q is true? Well, if I know P is false, then I should automatically be able to conclude that P implies Q is true. And what other true statement am I missing? Well, I need to take care of the P and Q part. And I'm saying, well, if Q is true, I automatically get P implies Q is true. So to convert P implies Q to a statement involving nots, ands, and ors, I can write not P or Q. Now, in order to negate, how do I negate a statement P implies Q? Well, in order to negate this, I can just look here and I can say not of not P or Q, use De Morgan's laws, put the not inside, so this I get P and not Q. And this should sort of make sense why this is equivalent to P and not Q. When is this statement true? Not of P implies Q. Or in other words, when is P implies Q false? It's precisely when P is true, Q is false. The only time when P implies Q is false is when P is true, Q is false. Therefore, if you were to show a counterexample for a statement of the form if P then Q, you would need to find an example where P is true and Q is false. If I happen to have a P if and only if Q, then this is simply P implies Q and Q implies P. P implies Q and Q implies P. And in order to negate this, I can simply just negate this statement. I can take so to negate P if and only if Q, I can negate this, so I can say not of this or not of this. And I can distribute these. So here I get a P and not Q, or Q and not P. And again, this should sort of make intuitive sense. When is P if and only if Q false? It's either when P is true and Q is false, or P is false and Q is true. P if and only if Q is false, when P is true and Q is false, or when Q is true and P is false. And so in order to find a counterexample for an if and only if statement, P if and only if Q, in order to find a counterexample for P if and only if Q, we simply need to develop a counterexample for either for which P is true and Q is false, or an example where Q is true and P is false. I'd like to move on to talking about predicates. Are there any questions so far about these identities? So in order to maybe give you a review about for all and there exists, I want to use an example from the practice questions. I'm not going to do the problem totally exactly, but I want to use that as a grounds for an example, which I hope will make clear this idea of for all and there exists. And in particular, instead of just talking about the definitions of for all and there exists, I want to focus on what happens when you have multiple predicates and how they're interacting with each other. I want to also give you some techniques about when you see these kind of expressions involving multiple predicates, how to reason about them and how to reason about them accurately. And so I'm going to write down this definition. So here we have, so I'm not going to be, so I would not worry too much about the content of this definition. The goal of this problem is rather to practice the logic of the quantifiers. So rather than worry too much whether or not you understand this actual definition, I would worry primarily about being able to understand the logic of the quantifiers involved in this problem. And So this definition says if we have a sequence, and the sequence of real numbers S0, S1 up to Sn, if we have the sequence of it converges to L if, I'm gonna write out this definition first. Now, if you were to be confronted with this expression, you might have a hard time of thinking about, like, what am I supposed to do? Like, how do I interpret this expression? And so first, I'm going to give you just an intuitive understanding before you even look at this web of symbols. So intuitively, you feel that a sequence of numbers converges to a limit, essentially, if it kind of like, gets close to it. So if, for example, if I have, say, like 1/2, 2/3, 3/4, and so on, like intuitively you feel this is converging to 1. Don't worry too much about it. If you're not clear about like convergence of sequences, this is that topic on its own is out of scope in this course, but I want to use that as a motivation for the example. So how am I going to look at reading this statement or reasoning about what's going on here? I said for all epsilon greater than 0, and I'm not even sure what epsilon is. I'll keep going. There exists this big N greater than 0. I don't know what big N is. I'll keep going. If little n is bigger than big N, then this is true. So what's little n? Well, little n is well, actually I shouldn't. Actually, the sequence goes on to infinity. So there are infinite number of terms in this sequence. But what's little n? Little n is the index of a term in the sequence. So n tells you like this is the first term in the sequence, or this is the 10th term in the sequence, the 100th term. Little n is the index of the term in the sequence. And what this is saying is, as long as my little n is bigger than my big N. So now if I'm imagining this, if I imagine this sequence, if I start to plot this here, all right, if this here is my little n, this is my index, and then I say, okay, here, this is 1, so, or is 1, I'll put it like 1/2, and then 2/3, 3/4, and so on. I'll plot them a little closer to each other. So it's probably something like this, and I feel like it's probably getting closer to the value of 1. It looks something like this. And so as I read this definition, I say, all right, the index has to be bigger than big N. If I know the index is bigger than big N, so that should clue me in that this big N is serving as some kind of threshold wall. And it's like sort of some kind of threshold wall for which, if I know that my index is bigger than this wall, this is true. Now, L is the limit of the sequence. This is sort of like what it's getting very, very close to. So L is here. And if I'm past this threshold wall, what do I know? I know that the values of the sequence are within epsilon of my limit L. In other words, if I pass this wall, the values of my sequence are within a buffer room of width epsilon, or within this kind of buffer room within epsilon of the limit. All my terms of the sequence are within this buffer room epsilon of the limit. And so here now I think we can have a more intuitive understanding, which is that for all epsilon greater than 0, so what's epsilon? Epsilon is my buffer room. Every epsilon, there exists this wall, big N, where past that, if I know I'm past that wall, all the values of my sequence are within this buffer room of L. Now, the one key thing I want to emphasize here is that when I say for all epsilon greater than 0, there exists this n bigger than 0 such that this property is true. This big N need not be the same for every epsilon. The way to sort of interpret this is to sort of read this one quantifier at a time. And I say for all epsilon greater than 0, what does that mean? It's whatever epsilon I have, there exists this big N where this thing is true for that epsilon. Maybe a different way I want to make this intuitively clear to you is when I read this, I'm saying for all epsilon greater than 0, it means whichever epsilon I pick, for that specific epsilon, there exists this big N where past that wall, I'm within epsilon. No matter which epsilon I pick, there exists this wall for which past that wall, I'm within epsilon. I think I've still been a little bit imprecise with the language, and so I want to make this very clear to you. When I say for all epsilon greater than 0, and like once I reach here in the statement, I'm saying for all epsilon greater than 0, so every epsilon has the property that there exists this n where this thing is true. When I say every epsilon has the property that, I'm not saying that different epsilons have the same n. I'm saying every epsilon has the property that there is this n that works for that epsilon. Yeah.
This is like an annoying semantics question.
Mhm.
Just there's a period after for every epsilon greater than 0 because that's the next predicate. But should there exist an element n greater than 0? Should that also have a period after?
Having the periods is not too much of. I wouldn't worry too much about. I put the period there as just a separator, but I wouldn't worry too much about whether or not you put the periods. It's just as long as it's clear, sort of where the for all scope is, and then where that there exists scope is, and where the rest of the property scope is. It's fine. So like even if I were to omit the periods, I think it's pretty still clear what the scope of the quantifiers are. Yeah. And so the way I want to think about this is I'm saying no matter which epsilon I pick, there exists this n for that specific epsilon. I could pick this epsilon and I can find a specific n. I could pick this epsilon and I could find a specific n. If I pick this epsilon, I can find a specific n. Those n's can be different among the epsilons, but every epsilon has the property that they have an n that works for them. Every epsilon has the property that there is an n that works for them. Now, a different way I want to say this is no matter what epsilon I pick, I can find an n that works for that specific epsilon. No matter what epsilon I pick, I can find an n that works for that specific epsilon. And you might be wondering, you're saying, wait a sec, isn't this a for all statement? Why am I talking about a specific epsilon? Where does the for all statement come in? Where does this for all come in? And the for all comes in because I said, no matter which epsilon I pick, regardless of which epsilon I pick, that's the for all, regardless of which epsilon I pick. By the time I reach here, I have already chosen this specific epsilon. And that specific epsilon, I need to find an n that works for that specific epsilon. And so that motivates why if you have a for all statement, in order to prove a for all statement, you write take an arbitrary epsilon. That is essentially the same idea as no matter what epsilon I pick, I can find the n that works for that epsilon. That's why when you prove a for all statement, you'll say take an arbitrary epsilon, and then you prove the rest for that arbitrary epsilon. Another way to put that is you're telling the reader, give me whatever epsilon you want, and I will show you that your epsilon satisfies this property. Because you have the confidence to let the reader pick whatever epsilon they want, and you can always show that it satisfies the required property. That's why every epsilon satisfies this property. I'd like to switch the order of the quantifiers and to show you the difference that this makes. There exists an n greater than 0, such that for all epsilon greater than 0, n greater than big N implies S of n. In this case, now I'm going to read the predicate from left to right. I'm saying there exists this n. There is this n. And what is true about this n? What is true about this n? Every epsilon greater than 0 satisfies that past that n, my sequence is within epsilon of the limit. And so here, if you look at this sequence, this is no longer satisfying here. Because this is saying I can find some n, I can find some wall n here, where whatever epsilon I pick, whatever buffer room, no matter how small I make it, all these terms are within the epsilon. And that's not true, because even if I were to pick the epsilon, pick the n here, see these are getting closer and closer. If I pick a really, really small epsilon, I can exclude some of these points out. Like no matter where I pick my n, I can always make a really, really small epsilon and exclude the points out. And so that's why this sequence 1/2, 2/3, 3/4 no longer satisfies this predicate. As I read it, I'm saying there exists this n. I have this value n. And what does this value n satisfy? Every epsilon satisfies this property. Every epsilon satisfies this property. So therefore, to prove a there exists statement, what do we have to do? We have to demonstrate an example. Demonstrate an example of n, and then show that that example works for this property. So we become very, much clearer when we talk about functions. But are there any questions about interpreting these two predicates? All right. Also want to talk about the negation of predicates, how to negate these statements. If I want to negate the first one, I want to put if I want to negate this, just like as in De Morgan's laws, when we do a negation, we put the negation inside and we flip the and to the or. I can move the negation inside and also flip the quantifiers. So as I move my negation into here, this thing becomes a there exists. As I move my negation into here, this becomes a for all. And then I can do negation of n. N implies 7 minus L epsilon. And in order to negate an implied statement, we went over how to negate an implied statement. It's that this has to be true and this has to be false. In other words, I can write this as there exists epsilon greater than 0 for all big N greater than 0, n big greater than n, and not of right. Everything here clear, thumbs up, middle, and thumbs down. Right. Are there any questions? Anyone want me to repeat something again? Yeah. Oh, yeah. Oh, okay. Yeah. Yeah. So, so the question was regarding talking about the contrapositive, and I want to maybe step away from the quantifiers and just talk about the contrapositive on its own. So maybe I'll put it right here with the propositional logic. So if I am, so here I'm going to talk about the contrapositive. If I'm given a statement P implies Q, the contrapositive of this is I switch the order of the P and Q, and I put negation signs in front of it. So if I have P implies Q, the contrapositive is I switch the order of Q and P, and I put negations in front of it. And the key fact to remember about a P implies Q and its contrapositive is that these are equivalent. In other words, sometimes if you want to prove P implies Q, it is easier to prove its contrapositive rather than the original statement itself. Any other questions? Yeah.
Just a bit confused about how you went for the sequence for all epsilon is greater than 0 to why you pulled out for some n is greater than 0.
Oh, for the negation?
Yeah.
Oh, for the negation? All right.
Not the negation, the second line.
Oh, the second line is a completely different statement. And they're not related. I wrote so this and this are not like correlated in any way. I wrote them down in order to demonstrate the difference between the two statements. But all right. All right. Are there anyone want me to repeat how to distinguish between the first and the second? So I think just one key thing to remember, you see a for all followed by there exists. That means that this value before the there exists, after the there exists, can change from epsilon to epsilon. So I'm going to use this example. If you see a for all followed by there exists, that means the n can change from epsilon to epsilon, but some n has to work for all the epsilons. Just the n's can be different from epsilon to epsilon. If you see there exists then a for all, that means that this n has to work for every epsilon. In other words, every epsilon has to have this n work for it. If I see a there exists, so if I see a for all followed by there exists, this value can change from epsilon to epsilon. If I see a there exists, then a for all, this value has to stay the same for every epsilon. So I think that would be the main kind of takeaway point between the switching of the quantifiers. Right, I'm going to now erase the board. And we're going to move on to talking about sets. Right, so I'd like to transition to talking about sets. And so what a set is simply a collection of elements, and without regard to their order or their quantity. And so if we have a set, a set contains elements, and we are only concerned with inclusion or non-inclusion of elements. At first, this may seem innocuous that we're just talking about whether an element is included or not included, but the confusion may start to arise when we're dealing with sets containing elements which are themselves other sets. And so in order to make clear these kinds of, so rather than just go over the basic definitions, I want to use an example, which I hope is particularly tricky and confusing, in order to demonstrate to you different ways of manipulating these things in order to resolve any kind of confusion that you might have. And especially when you have sort of elements that are themselves sets, it becomes difficult to keep track of, say, like what's the union and intersection and power set and all that. And so I'm going to use this example here. I'm going to have, and this is taken primarily from question 1 of the practice questions that I prepared. So I have a set A0, that is the empty set. A set A1, which is defined to be A0 union the set containing A0. Before I even get to calculating exactly what this is, I think one key theme in manipulating sets, and if you look at your practice exam and what will likely show up on the real exam, is that you'll be given a few sets and then you will have to manipulate or write out the sets pertaining to like various set operations of A, B, and C. One thing that's really important when you're dealing with sets is to identify clearly what actually are the elements of the set that you're talking about. Sort of the first step to really make it really clear for you what's going on is to identify really clearly, these are the elements of my set. And so if I look here, A1 is equal to empty set union the set containing an empty set. It's maybe already kind of confusing, but I'm going to look at what my elements are. In order to take the union, you just want to, in order to take A union B, you want to identify the elements of A, elements of B, and put them together in one big set. So you want to put together elements of A and elements of B in one set. So if I look at A1, I have A union B, so I have two sets here. What are the, so I'm going to put them all into one big set. I'm going to take the elements here, I'm going to put them in here. I'm going to take the elements here, I'm going to put them in here. What are the elements of my empty set? No elements. Not going to add anything. What are the elements here? This is a set containing, this set has one element. That element is the empty set. And so I'm going to take that element and I'm going to put it inside. So I have two sets here. I'm going to identify the elements in each of the constituent sets. The elements here, there are no elements, so I add nothing. This set has one element, empty set. I'm going to add it in to my set. Do a second example. A2 is equal to A1 union the set containing A1. What is this? Well, I'm going to identify my elements in A1. There's one element, empty set. I'm going to put it inside. I'm going to go to this set. This set also contains one element. That one element is the set A1. I'll put it in here. And what is this equal to? I can expand this out. Is this and A1. Especially if you're confronted with a set as complicated, like sort of gnarly looking as this, you really want to identify what are the exact elements of the set. How many elements does this have? There are 2 elements. First one is here, second one is here. And then you can apply these rules like a union very, very systematically by writing out, one element at a time. Similarly, for A intersect B, you do the same thing. You just find the elements which are in both sets, which are in A and B. And so if you have identified the elements in A and you have identified the elements in B, it would be very easy for you once you just look at here are the elements in A, here are the elements in B, and you just look at, okay, which element is in both, which elements are in both A and B. I want to caution you of something. An element, say if I have an element A and I have an element like this, set containing A, these are not the same element. If I have a set like this and I take the union, this is a set. What are the elements here? Actually, not the union. Let's do the intersection. What are the elements here? There's one element, it's A. What are the elements here? There's one element, set containing A. Is there an element? What elements are in both sets? There are no elements inside both sets because this element is A, but this doesn't contain element A. This contains set containing A. And set containing A is not the same thing as A. And vice versa, that set containing A is not the same thing as A. So set containing A is also not in the set. Right, there's a similar procedure if you do a set difference, say A, set difference B. Move this up a little bit. So of course, you just find elements which are in A, find elements which are in A, and not B. I'd like to talk a bit also about subsets. And actually, before I talk about subsets, all right, yeah, maybe I'll talk about subsets first. So if I want A to be a subset of B, how do I test if A is a subset of B? Again, you identify the elements in A and the elements in B. And then for each element in A, you ask, is that element also in B? If you ever answer no to this question, so if you ever answer no, then A is not a subset of B. Conversely, if you ask this question for every element A and you answer yes for every single one of the elements, so if you answer yes every time, or for every element, then A is a subset of B. So in other words, you go through each element in A and say, is this element in B? Is this element in B? Is this element in B? If you ever answer no, if you even answer no for one of the elements, then A is not a subset of B. To do this, I want to demonstrate an example. I'm going to switch the boards. And here, maybe I'm going to take a set like this and ask, is this a subset? Is this a subset of, say, A2? A2 is this. First thing we do, identify the elements. This is one element. This is two elements. And then I ask, every element in here, is this also an element inside here? It is. This is an element also here. And so therefore, this is a subset of this. Maybe I'll give a different example. Is the null set, is the empty set a subset of this? What are the elements here? No elements. What are the elements here? This. So if there are no elements, is every element inside this set also inside here? Yes, namely no elements. So is every element inside here also inside here? The answer to that is it's vacuously true. The answer is yes, because there are no elements, because there are sort of no elements to ask that question. And so the answer is yes. And so as a generalization, the empty set is a subset of every set. And yeah.
That's what I was gonna ask. Isn't an empty set the subset of every single set? Even if you don't put an empty set element there, it's still a subset of it.
Right. So the empty set is also a subset of empty set.
Okay.
No, I think you're gonna sit back.
Right.
That's a good.
Yeah, I think that's what this is, yeah, this is like. It's
So one thing is that it's yeah.
That's the other way around it works for vacuum spaces, like every set is subset of the set.
No, every set is not a subset of the empty set, because even if as to your question, is every set a subset of the empty set? If I have a set 1, 2, 3, is that a subset of the empty set? The answer is no, because I look at the elements here, 1, 2, 3, and I say, is 1 an element inside the empty set? The answer is no. Therefore, this is not a subset. Not a subset. So it may be tempting sometimes when you have very simple sets like 1, 2, 3 to be able to just look at the answer and just like do it intuitively. But I believe on the test it will not be. There will not only be very, very elementary examples of just numbers. There will probably be other things just to sort of trip you up. And so in order to prevent getting tripped up by what are the sets and what are the elements, I think it would be important to follow these rules of really like first thing really, really clearly identifying what are the elements and then proceeding from there. I want to also talk here about the power set. The power set of A. This would be the set whose elements are the subsets of A. I want to do this as first as an example. So let's say a power set of A2. Let me remind you what the power set, what A2 is. So in order to calculate the power set, so what is the power set? Well, it's a big set. And what are the elements? The elements are all the subsets of this set inside here. And so the procedure to do this is first, almost every time, the first thing is to identify the elements. And then the second thing is to write out sets of every combination of inclusion or non-inclusion. So you identify the elements, I'll say of A. And then the second step is to write out sets, these sets. So write out a bunch of sets. And what do you want these like bunch of sets to satisfy? You want to sort of give every combination of inclusion or non-inclusion of elements of A. Let's do that here. What are the elements of the set? Here's one element. Here's a second element. So here's element 1, element 2. Now, what sets do I have to write out? I have to write out the sets for every combination of inclusion or non-inclusion of the elements of A. And so in order to make this really, really clear, I'm going to make a table. I'm going to make a table. And let's do this. I'm going to make a table. And I say element 1, element 2. So what's every combination of inclusion and non-inclusion of elements of A? I got both non-included. This one, only number 1 included, only number 2 included, or both included. Now, if I had 3 elements, I would do XXX, XX check every combination of, whether something can be included or excluded from, whether something can be included or excluded. And I write out the corresponding set. So here I have no 1, no 2. That's empty set. I have yes 1, no 2. So I have one element, this. So I write out a set. So the key thing is I have to write out a set. And that set contains, and this sort of enumerates what are the elements of this set. So I'm going to write a set, just to make it clear. I'm going to write a set. What elements do I put here? I don't put 1, I don't put 2. Finished here. So this is empty set. I write another set. What elements do I want to put inside here? I want to put an element 1, but not element 2. I write out another set. No element 1, yes element 2. I write another set. Yes element 1, yes element 2. This list here now gives you the elements of the power set. And so how do I actually write out the power set? Well, the power set is a set. What are its elements? It's these 4 things that I listed here. So the first element is empty set. The second element is set containing empty set. Third element is set containing empty set. Fourth element is set containing empty set and the set containing the empty set. I learned this once in high school. And I was falling asleep in class, so I decided to stay awake. I would count the number of times the teacher said the word set. But I don't think anybody was counting. I actually stayed awake and I counted 104 times that he said the word set. And I told him and I made it on Twitter. But anyway, but the procedure here, I hope this procedure is clear. Almost every time, first thing, identify the elements inside the set. And then make this table 1, 2, and say, not included, or so like both not included. This one's included. This one's included. Both included. Every combination. Write out all of these elements. Those are the elements of the power set of A2. So what is power set of A2? It's a set containing elements, and those elements are the ones listed here. Now, sometimes it might be the case you have an infinite set or a set which is too large, and it's impossible to therefore write out all the elements of your power set. In other words, like if you were to be given a set containing 7 elements, you would then have to write 2 to the 7, 128 elements for that set, and that might not be feasible on the exam. And so I want to give you one sort of guiding principle about reasoning about the power set. Notice how when we do these set operations, the first step that we do is always to identify the elements. So it will be very, very helpful to have a clear idea of what are the elements of the power set. The elements of power set of A, the elements of power set of A are the subsets of A. Therefore, I want to have a little more space. Is it okay if I erase this? Yeah. Therefore, if you are presented with, say, identifying whether something is a subset of the power set, what if I say, is this a subset of the power set of A2? What do? I identify the elements here. What are the elements of power set of A2? They're the subsets of A2. And therefore, I go through and I say, is this a subset of A2? In other words, I'm testing for subset here. So I'm saying, is this element an element of power set of A2? Now, elements of power set of A2 are subsets of A2. So is this an element of power set of A2? Same question is this a subset of A2? Yes. Is this a subset of A2? Is this subset of A2? Now, how do I answer this question? Well, I identify the elements in this. Is this a subset of A2? So how do I answer this question? I identify the elements here. I say, is this element an element of A2? This is an element of A2. Therefore, this is a subset of A2. And so since I answered yes to both questions, this is a subset of the power set of A2. Anybody want to hear the explanation for this again? Thumbs up. So how confident do you feel about this example? Thumbs up, middle, thumbs down. All right, good. One more topic about sets. Let's this up. One more topic here I want to mention is that of the Cartesian product. The Cartesian product A cross B. I'm going to write out the formal definition first. What is the Cartesian product? I want to give you like intuitively. It's a set. Cartesian product here is a set. Its elements, ordered pairs. What do these ordered pairs look like? The first element inside the ordered pair is an element of set A. The second element is an element of set B. I want to give you an example. Let's say I give you A2 cross A2. What is this? Well, this is a set first. And how do I might not have enough space here, but what is the set? So how do I calculate A2 Cartesian product A2? It's the elements of them are ordered pairs. The ordered pairs, the first one is an element of, let's do A2, A1. The first element in the ordered pair is an element of A2. The second element in the ordered pair is an element of A1. So how do I do this? Well, first thing, identify the elements clearly. A2, I'm going to rewrite this here as this. A1 as this. And so what are my elements? Here's one element. Here's a second element. Actually, A1, I think. A1 is this. Sorry about that. And what's my element here? That's an element. And so how do I form these ordered pairs? It's every combination of first thing is inside here, second thing is inside here. Every combination, first element has to be inside my A2, second element has to be inside my A1. Every combination of elements that I can do. So I can do this, or this. So first element here, empty set, or I could have done this, set containing empty set, comma, empty set. Yeah.
Can you make a Cartesian product where one of the sets is the empty set?
Oh, yeah. Right. So if you have a Cartesian product of so if you have a Cartesian product, say empty set Cartesian product 1, 2, 3, we're going to do the same procedure. It's a set. The elements are ordered pairs. What's the property of these ordered pairs? The first thing is an element here. Second thing is an element here. So I can't get any ordered pairs out of this because the first thing has to be an element here, but the empty set has no elements. Therefore, I can't get any ordered pairs. Therefore, this equals to the empty set. And therefore, you can probably conclude from here the empty set Cartesian product anything let's say A equal to the empty set. Any other questions about this? Yeah.
So Cartesian product is a set.
Okay, sorry.
Is Cartesian product set? Set?
Oh, like A cross, like A X A.
Is a Cartesian product a set?
Yes. So a Cartesian product. So a Cartesian product is itself a set. The elements of that set are these ordered pairs, such that the first element in the ordered pair comes from the first set. Second element in the ordered pair comes from the second set. One other thing to realize is the Cartesian product is not commutative. If I have A cross B, this is not the same as B times B. A product B is not the same as B product A. The way to realize this is because the elements here are ordered pairs. The first has come from A, the second has come from B. Conversely, here, the elements are ordered pairs. The first comes from B, the second comes from A. Yeah.
Well, taking the Cartesian product of two sets, if any of those sets is an empty set, then the result is an empty set.
Yes. Yes. Just want to do one more example to combine all of these. I can also write the directions for computing the Cartesian product. First thing, of course, is to identify elements of A and B. Second thing is to form ordered pairs for every combination of basically here is so here would be an element in A. So this would be an element in A. Here would be an element in B. Form ordered pairs, every single combination of element in A, element in B. And then 3. Then the step 3 would be to combine all these, ordered pairs. As elements in a set. One last little thing I want to cover is, let's say we have a combination of these, and let's say we do the power set of a Cartesian product. So for example, let's do the power set of Cartesian product A2, A1. Again, how do I calculate the power set? I identify the elements inside the set. Here's one element, I call the element 1. Here's one element, I call the element 2. And what is the power set? It's a big set. What are the elements of this power set? They are subsets of this set. So let me first write out the subsets of this set. So subsets of A2, A1. How do I find these subsets? Well, they're individual sets, and I want to write every combination of including or not including elements 1 and 2. So here I write not including both. So this is like an XX. So 1 and 2. Then I do check X. This is the set containing this. I want to do X check. This would be the set containing the second element here. And then I want to do check. And that would be the set containing both of those elements. So what is my power set? I've now written out each of these subsets. These are all subsets of A2 cross A1, and therefore, because they are subsets of A2 times A1, they are elements of power set of A2 times A1. So these 4 things are the elements of this set, and I can now list each of these. So this would be the empty set, actually. Empty set, then this, then the one on the bottom, and then this one, I'll just do that. Any questions so far? All right. The next topic I'm going to do is regarding the formalism pertaining to graphs. And then, yeah.
Can you go over set builder notation?
Oh, set builder notation. All right. So I just want some. So the set builder notation, I don't have an example necessarily prepared for this, but I'm gonna like maybe make up an example. N such that let's say we do S such that S is maybe N such that N is a multiple of 5. And so the way to interpret the set builder notation is here I write a variable, and this variable effectively serves like the role of like a dummy variable. And this dummy variable, what information I can find out about this dummy variable is located after this such that, or this colon, or sometimes it's a colon or a vertical bar. What's the property of the, so this dummy variable says, these are my elements in my set. And what are those elements of the set like? Multiples of 5. My set contains elements n, where n is a multiple of 5, and therefore this is essentially 0, 5, -5, 10, -10, and so on. Is that good? Any more questions about the set builder notation? So you can also specify a set of sets. Like if I want to say, I have a set containing S where S is a subset of A2. That means my elements of this set are, I'm going to call them a variable S. And what do my elements look like? My elements are subsets of A2. This is the power set, A2. I want to very quickly talk about the formalism also for graphs. What is a graph? A graph G. It's an ordered pair, V, E. What are each of these things? V is a set. It's a set of vertices. What is E? E is also a set. It's a set of edges. And to give an example, let's say I have a graph that looks like this: 1, 2, 3, 4. V is a set of vertices. 1, 2, 3, 4. E is a set of edges. Now, if this is undirected, it's undirected. E is a set of edges, and I express the edges as 2-element sets. Why do I express the elements as 2-element sets? Because I don't care whether I say 1, 2, or 2, 1. The order is not relevant. And remember, in sets, the order is irrelevant. So therefore, I can express this edge in terms of a 2-element set, say 1, 2, and another one would be 1, 4, and here 2, 4, and 2, 3. Now, what if they were directed? If they were directed, I can no longer express each edge as a set, because the set doesn't capture the ordering of the vertices. It doesn't, like if I made this directed, I can no longer capture 1, 2. I can't capture the information here because 1, 2 doesn't tell you, am I going from 1 to 2 or 2 to 1? And so when it's directed, we again have a set of edges, but now we have a set of ordered pairs. And the ordered pairs say, I'm going from here to here. So I'm going from 1 to 2, or I'm going from 2 to 4, or I'm going from 1 to 4. I'm going from 3 to 2. last thing to talk about here about graphs is that it could be the case where the vertices, where the labels on the vertices are not such simple, say numbers 1, 2, 3, and 4. They could very much be some quote unquote higher order or objects. It's possible I can make a graph that looks like this, which has ordered pairs 1, 2, and then here 2, 3, and here 1, 4. Let me make them ordered pairs. It's nothing sort of new. It's just that this might require like a second level of abstraction. What are my vertices here? Well, my vertices are a set. What are the elements? Each of these labels. 1, 2, 1, 4, 2, 3. What are my edges? My edges, this is a directed graph. The edges, what are my edges? My edges are a set. Elements of the set are either sets or ordered pairs. This is a directed graph. Therefore, we have the elements are ordered pairs. What do my ordered pairs look like? I tell you from which vertex to which vertex I'm going to. So I go from 1, 2 to 2, 3. Sorry, 1, 2 to 2, 3. And what else do I have? I also have another edge. Where am I going from? I'm going from 1, 2 to 1, 4. So how did I write out all of this? What are my vertices? My vertices are the individual label. My vertices are a set. The elements of that set are the individual labels. I also have a set of edges. What is E? E is a set. The elements are edges. Because this is directed, the elements are ordered pairs. If they're undirected, they would be 2-element sets. These ordered pairs tell me from this vertex to this vertex, from 1, 2 to 2, 3. This one is from 1, 2 to 1, 4. Yeah.
Question about the problem 3 of price freedoms.
I didn't necessarily read it very carefully, so I don't want to answer it like in real time, but we may answer it after. If that works, yeah. Yeah.
For directed graphs, shouldn't it doesn't matter if you use E edges or A arcs? Doesn't it?
Sorry. Oh, like the letter, is it E or K or?
Is it like graph equals VA or VE?
Yeah. So the letters is not too important, other than actually, typically we use V. Well, what variables I use here are not too important. Like what variable, what the actual letter is here. I could write A, B, and if I wrote A, B, then I would know that A is the set of edges. A is the set of vertices. B is the set of edges. So which letter I use, V, E, or A, is not really too important. Yeah. Yeah.
Are we gonna get like operations on graphs and here? Like, can we go over like some operations on graphs?
I don't have anything prepared off the top of my head of a product of 2 graphs. Is that something that you covered in?
Completely new that came
In the practice or?
practice side.
So the product of 2 graphs, that's not a sort of like standard terminology that you were expected to know. In other words, the test said this is what the box product of 2 graphs means, and it gave you the definition. And so the exercise is not so much that you had to know anything about. So box product is probably not even a real concept. He just made it up for the test. But the intent of the question was not so much that you could walk into the test and know what a box product was immediately, but instead it was to be able to parse the propositional and predicate logic and the like the language in order to formulate such a graph. All right. I want to move on from this. I'm going to erase both boards, and then I want to move on to induction.
Yeah.
All right, so for induction, I want to jump directly into an example. And from that example, I want to show you, so after we graded the homework, I want to show you many of the places in which you should probably avoid to avoid losing points. Some of these things are legit. Some of these things are a little bit pedantic. In other words, like after this class, you might not actually use such strict rules and to write an induction proof. But the reason for the maybe pedantic restrictions is so that those restrictions are put into place that you have a clear understanding of the concept of induction. So I also want to give you sort of a clear step-by-step instruction on how to write these proofs in order to get the maximum number of points on the exam. For that, I want to use an example. So this is question number 4 on the practice questions that I prepared. And so what this says, I want to, I'll write it here. We have if f0 is equal to 0, f1 is equal to 1, we have the recurrence f of n equals to fn minus 1 plus fn minus 2. This is for n greater than or equal to 2. And we want to prove f of n is equal to p to the n minus q to the n over square root 5 for all n in the naturals. And what's p and q? P and q are the solutions. P and q are the solutions to the equation x squared equals to x plus 1. I want to first, by writing down, so step 1, inductive statement. Now, what is the inductive statement? Notice I am proving something about n for every n natural number. The inductive statement is a statement about specific n. The inductive statement is a proposition. So remember, this is a proposition. This is a proposition. And I'm saying this proposition for a specific n. What is this proposition? It's that f of n is equal to p to the n minus q to the n over square root 5. A key thing to remember, p is a proposition. Therefore, if I were to write p of n equals p to the n minus q to the n over square root 5, this would be incorrect because p is a proposition. P to the n minus q to the n over square root 5, that is an algebraic, these are algebraic variables. They are essentially take on numerical values. P is a proposition, and essentially takes on Boolean values. I cannot set a proposition equal to essentially what is a number. Why is this a valid mathematical statement? I'm saying P of n is the statement that f of n as defined here, equals to this formula. This is a Boolean value. Is f of n equal to this formula? Is it equal for n equals 0? Is it equal for n equals 1? So P of 0 is this equal to this for n equals 0? P of 1 is this equal to this for n equals 1? P of 2 is this equal to this for n equals 2? Notice that P of n is referring to a specific n. What is P of n? It's this whole equality. Whether or not something is equal to one another is either true or false, and therefore that can be a proposition. P of n, we're referring to a specific n, is f of n equal to this formula P of n minus Q of n over square root 5. Notice because I am talking about a specific n, I do not write for all n in the natural numbers here. If you write for all n in the natural numbers here, that will be an incorrect inductive statement. So notice I don't write this, and I don't write this. All right, second thing, I'm going to do a base case. And what is my base case here? I'm going to say I'm going to do P. So I'm going to prove this for all natural numbers. So my smallest natural number is 0, P of 0. What's P of 0? Well, I'm going to plug this. So it's very easy. All right, P of 0 equals to P of 0 minus Q of 0 over square root 5 equals to 1 minus 1 over square root 5 equals to 0. Check. This is not a correct statement. P of 0, remember, is a proposition. This is a number. I'm trying to prove P of 0. So I'm going to say I want to prove P of 0. And how do I prove P of 0? The right-hand side is equal to 0. The left-hand side is equal to 0. Therefore, f of 0 equals to, say, P of 0 minus Q of 0 over root 5. Check. Another thing I didn't do is I didn't write f of 0 equals to P of 0 minus Q of 0 over root 5, and then simplify this to be like, this is wrong. Why is this wrong? What I want to show is that f of 0 equals to P of 0 minus Q of 0 over square root 5. A proof always starts from what you know and goes to what you want to show. A proof never starts from what you want to show and goes back to what you know. Here, I started from what I wanted to show and got back to something I knew. Therefore, this writing is not a valid proof. If you were to write something like this, at least you want to write an arrow saying read from bottom to up. I go from something I know to something I want to show. All right?
Yeah, it's very good.
The next step, step 3, inductive hypothesis. And this comes in conjunction with the inductive step. Now, what is the inductive step? The inductive step is that P of n implies P of n plus 1. In other words, if I know that P is true for specific n, I'm guaranteed that it's also true for specific n plus 1. Why does this work? Is because I start with the base case and I say, I know P of 0 is true, and then I prove this implication. When I prove this implication, I say, if I know a specific value n is true, I know it's also true for n plus 1. And I prove a base case, P of 0 is true. I know it's true for 0. Therefore, I can conclude it's true for 1. Now I know it's true for 1. I can apply this again, and therefore it's true for 2. Now I know it's true for 2. I can apply this again, and I know it's true for 3. Now, so the inductive step is this implication, is this implies statement. If I know this is true for specific n, then I know it's true for that value n plus 1. As I also said, this was a specific n. So therefore, when you assume, so what is your inductive hypothesis? It's what you want to assume in your inductive step. Remember, an if statement, how do I prove it? I assume this, I conclude this. So I want to assume P of n. What is P of n? I'm going to assume P of n is that f of n equals to P of n. Notice because I said the P of n is for a specific n, I don't write for all here. This is incorrect. Why is this incorrect? It's because we actually want to prove this is true for all n inside the naturals. And if I assume that, I've essentially just assumed what I wanted to prove. I'm not assuming this is true for every n. I'm saying, assume this is true for some specific n. Can I show that it's also true for n plus 1? Now, yeah.
Can we say there exists an n that is true for that?
No. the safest thing is just to say assume f of n is this, or you can say for some n inside naturals. I think this would be the safest thing to write.
It's not true.
Now, so here I'm going to try to prove p of n plus 1. And what is it that I want to show? I want to show that f n plus 1 equals to p to the n plus 1 minus q to the n plus 1 over square root 5. It's always helpful right here in your moving from inductive hypothesis to inductive step to have a clear idea of what I'm assuming, what I'm proving. How do I know this? This is an implied statement. My inductive step is essentially proving an implication, assuming this, which is my inductive hypothesis, and proving this. Now I want to prove this, f of n plus 1 equals to this. And you might be tempted, as before, to start with this and then kind of simplify it on both sides and get to something you want to do, get to something like 0 equals 0. If you do that and do not write the up arrow signifying that you're to read from bottom to up, that would be a backwards proof, and that would result in quite a bit of deduction. If you started with this and kind of simplified both sides down, you essentially started from what you wanted to show and got to something you know. That is not a valid proof. A proof always starts from what you know and gets to what you want to show. Another way to prove such an equality is to start from one side and then kind of work your way like equals all the way to the other side. And so I want to demonstrate that here. And why is that not a backwards proof? It's because when you start from one side, you should do your equals all the way to the other side. You don't assume that these two are equal. You just started with this and say, well, I know this is equal to this, is equal to this, is equal to this. And finally I got to here. And then I therefore prove that this is equal to this. But it's not like you assume starting that these two were equal. F of n plus 1, what is f of n plus 1? It's f of n plus f of n minus 1. Use my inductive hypothesis. This is p to the n minus q to the n over square root 5 plus p to the n minus 1 minus q to the n minus 1 over square root 5. Now I can combine the common denominator, square root 5. Here I have a p to the n times, there's p to the n times 1. I'm sorry, p to the n minus 1. So I have p to the n minus 1 times 1 plus p minus q to the n minus 1, 1 plus q. How do I get here? I just factor, so I have p to the n minus 1 times 1, that gives me this. P to the n minus 1 times p, that gives me this. Q to the n minus 1 times 1, that gives me this. Q to the n minus 1 times q, that gives me this. What's 1 plus p? Remember, p and q are solutions to this equation. So 1 plus p is equal to p squared. So I write p to the n minus 1 times p squared minus q to the n minus 1 times q squared over square root 5. And if I combine these with the exponents, I get p to the n plus 1 minus q to the n plus 1 all over square root 5. I've shown this is equal to this, this is equal to this, is equal to this, equals to this, all the way here. Therefore, this is equal to this, and I've gotten what I want to show. This problem is not quite finished. You might think, oh, I can, step 5, conclusion. Since we had since f of 0 is equal to 0 and p of n implies p of n plus 1, therefore p of n true for all n. How do I write this conclusion? You say since base case and inductive step, therefore p of n. Remember, p of n is a proposition for specific n. What we want to prove is that proposition p of n is true for every n. And so I have to say, therefore, p of n is true for all n in the natural numbers. This part is key. Yeah. Mm-hmm.
Since the recurrence relation is defined, right, f of n depends on the previous terms, we need like two base cases, there would be like a strong.
Right. So I intentionally did this to
prove P of n.
semi lead you astray to show you how to necessarily to like correct it. Yeah, and so this proof up here is not entirely correct. In fact, this is like it's kind of wrong. And I did this in order for you to, because your first instinct when you do an induction proof is probably just to do this kind of assume P of n, get to P of n plus 1. Your first instinct is to do that. But in this case, this is not a totally correct proof. Because, and I'm about to show you why this is not a totally correct proof. But a priori, before you start the proof, you may not necessarily immediately have known that you had to make these corrections. In other words, these corrections, I did this in this order in order to show you how you would, as you progress through working through the proof, realize that you had to make some corrections. And as was correctly pointed out, the error here lies in the fact that when I do my inductive step, I'm saying I'm assuming P of n and I'm concluding P of n plus 1. Remember, P of n is for specific n. As I do this, notice how I replace f of n minus 1 with this formula. This replacement was never assumed. I only assumed P of n, which is that f of n equals to this, but I never assumed P of n minus 1. Therefore, this substitution is invalid. So one thing to pay attention to when your inductive step is that as you're using your inductive hypothesis, am I only using the one right before, or am I using stuff even farther before that? Here, you notice I'm using stuff farther before that, which means I can't just use this regular induction here. If I'm using, notice here in my inductive step, I'm using two, so I need sort of not just the one preceding, but I need one preceding and two preceding. If I have two preceding, if I only use one preceding, this whole thing is fine. But if anything more than one preceding, I need to strengthen my induction hypothesis, and I need more base cases. Reason for that is, I think about how this induction works. I have P of 0, and I want to use P of 0 to conclude P of 1. So let's say n equals 0. And I say P of 1, okay, I want to now conclude P of 1. So I want to use P of 0 to conclude P of 1. So n is 0 now. This relies on n equals 0, and this requires f of 0 and f of negative 1, which doesn't work. Right? So I actually needed to establish not just P of 0, I also needed to establish P of 1, so that now when I enter into this inductive step, I want to prove P of 2. What's P of 2? That's n equals 1. N equals 1, I can now use f of 1 and f of 0. And I have f of 1 and f of 0 because I proved two base cases. So therefore, the way to realize this is if my recurrence relies on two elements preceding. So two elements preceding means that I need two base cases. And then you also need to strengthen your induction hypothesis. I'm going to first do this correction by correcting the base case. So I'll put this right here so that I don't have to move the board. So this is part 2b. This is another base case. I need two base cases, so I'm going to do P of 1. What's P of 1? So f of 1 is equal to 1. My formula gives p to the 1 minus q to the 1 over square root 5. If you look at the values for p to the 1 minus q to the 1, should be square root 5 over square root 5. That equals to 1. So there I've gotten my second base case. Now my inductive hypothesis, I can't just assume the one for p of n, because I need the one for p of n and I need the one for p of n minus 1. So a convenient way to do this is just a strong induction. Suppose f of k equals to p of k minus q of k, or for every k, for every 0 less than or equal to k less than or equal to n. My inductive hypothesis is not just assuming p of n. I'm saying assume everything up to n. Assume p of 0, p of 1, p of 2, p of 3, all the way up to p of n. And why that is useful is that now that I've assumed p of 0, p of 1, p of 2, p of 3, all the way up to p of n, when I prove p of n plus 1, I can use p of n, I can use p of n minus 1, I can use p of n minus 2, I can use all of those, even though in this case p of n minus 2 and further is not necessary, but it just helps to be more convenient to do this. And, alternatively, you could also say assume say P of n and P of n minus 1. And you also would want to specify that n is at least 1. If you don't specify this, then P of n minus 1 becomes invalid for n equals 0. So both of these are valid assumptions. So now my inductive hypothesis is no longer P of n. My inductive hypothesis is P of 0 and P of 1 and all the way up to P of n. And then I want to show P of n plus 1. And so here I have f of n. And so this essentially now follows directly because now that I have assumed P of 0 and P of 1 and all the way up to P of n. Remember, an and statement, if I assume it, I can use all of its individual ones. So I can use P of n individually to do here to here. I can use P of n minus 1 individually to do here to here, and the rest is algebra. Yeah.
In your inductive step, you use your inductive hypothesis as P of n that implies P of n plus 1. Is that correct?
Yeah, so the inductive step now is P of 0 and P of 1 and all the way up to P of n implies P of n plus 1. So I've changed the inductive
Hypothesis is saying that f of k equals P of k and Q of k. So like, where is the assignment of P of n to f of k? Because f of k and P of n, like if they are not assigned to each other, how are they?
So this, I'm saying this is a shorthand for saying f of 0 equals to this, f of 1 equals to this, f2 equals to this. So f0 equals to this, that's P of 0. So I'm indexing my k, and my k can go for anywhere from 0 to n. So if for k equals 0, then I get f of 0 equals to this. That's the same statement as P of 0. And if k equals 1, I get f of 1 equals to this. That's the same statement as P of 1. If k equals 2, yeah. So sort of this is a short encoding of this proposition. Yeah.
Like you said, the range from 0 to n, just like the P of 1.
The reason I can so actually I don't even need so the reason I can modify this is not even because I added a new base case. The reason I can always actually assume this. You can always assume this, no matter how many base cases there are. The intuition here is that now I did P of 0, I did P of 1. So now I can do this. If I prove this, I have P of 0, P of 1, that gets me P of 2. So now I have P of 0, I have P of 1, but that got me P of 2. So now I have P0, P1, P2. Now I come back here, P0, P1, P2 can get me P of 3. Then I do P0, P1, P2, P3. I have all 4 of them. That can imply me P of 4 and so on. Yeah. Yeah.
For the inductive hypothesis, didn't you specify that n has to be greater than or equal to 1?
Sorry?
For the inductive hypothesis, shouldn't you like add that n has to be greater than or equal?
Oh, here?
Yeah.
Oh, yeah. Yeah, that's a good point. So maybe here we write n greater than or equal to 1. Yeah.
Okay, so I guess now, because if we're assuming that anything less than n is going to be true,
Mhm.
why is it that we now need more base, why do we need P of 1, but we don't need P of 2 if we're assuming everything below n?
Oh, I see. So why do we not include a base case P of 2, P of 3, P of 4 all the way?
Yeah, but we do need P of 1, right?
Right. Yeah. So the reason why we need P of 1 and P of 0 is we can try to. So this inductive step is very general in terms of it's like I can kind of. I know I said this with specific n, but the idea is that I can use this inductive step for n equals 0. I can use this inductive step for n equals 1. I can use this step for n equals 5 or n equals 7. It's just that when I use this, I'm using it for one specific n. I don't apply this inductive step sort of on one shot, apply on everything. I use it on a specific n, but I can put any n I want inside. And so one way I can think about this is why do we need the 2 base cases? Is to kind of trace this inductive step for a small case. So if I have P of 0 and P of 1, I would want that to give me kind of P of 2 in my inductive step. Let's trace that. If I have P of 2, if I want P of 2, that means I need n is equal to 1. And if I have n equals equal to 1, I would need n is equal to this. I would need this part. That would be the P of 1 part. And I would need this to be the P of 0 part. Now, why would I not need a base case for P of 2 is because when I have P of 1 and P of 0, I can run this whole thing down, and then I can get f of 2 equals to sort of this, and I can get P of 2. So my method of getting P of 2 is using my inductive step, flowing through the inductive step, using P of 1 and P of 0. Yeah.
But what if you don't know how far back you're going to have to use, like what if you don't know what that n minus?
Oh, like if you don't know, so here we knew it was 2 back, but what if you don't know how far back you have to go? Right, so how I was able to tell how far back I was needed to go was, notice how like I did the inductive step first before I went back to do the corrections. When you derive out the inductive step, you kind of see what you need to get through the whole thing. Right.
Because, like with graphs,
Mhm.
you don't always know how many edges you're gonna have to take out. It's like, I'm thinking of like a question where you had to remove a cycle, but that cycle could have an arbitrary number of edges.
Ah, I see. It's a good question. Like if you have a graph and you have to remove a whole cycle, you don't know how far back you have to go. I'm trying to come up with a reasonably simple answer to this question, which is, I think like one way you can tell is to also do this kind of tracing, because if you have a graph, they have 2 edges, there kind of aren't that many combinations of graphs with 2 edges. And then usually what happens is that if you have a graph with 2 edges, like you can't remove that many edges back. Like, and so I think what the idea is, if you have a graph, sort of the background idea is, say you use this like strong induction hypothesis where you say edges, 0 edges all the way up to n edges. And you don't know at n edges whether you like go back, 1 edge or 2 edge or 3 edges. But what you do know is that you never go back past, say, 0 edges. Right? You wouldn't go like underneath 0 edges. You wouldn't have -1 edges. And so sort of the intuition is what you'll see is probably going to happen is that at 1 edge, if you trace through your inductive step, you'll only rely on, say, the 0 edge case. And then maybe if you do 2 edges and you trace down your inductive step, you only rely on the 1 and 0 case. And if you see that, if you can use your like 1 case, trace it through the inductive step, and only use your 0 case and nothing breaks, then you really only need 1 base case, because you only needed your P of 0 because my inductive step took care of the job for P of 1. But if you trace through your P of 1 case and you realize you needed like 0 and -1, then you're saying, okay, maybe I need a 0 and a 1. I know that there might not be a totally satisfactory answer, but I think the idea is to start with your small cases 0 and 1, 0, 1, 2, trace them through the inductive step, and then see what you need to proceed it. If you do P of 2, you trace it through your inductive step and you require P of 1 and P of 0, and nothing breaks, like you don't ever need a P of -1 or something crazy like that. You do a P of 2, trace through your inductive step, and you never need P of -1, nothing breaks. That means that your P of 2 is completely handled by your inductive step. You won't need to give a base case for P of 2, because as long as you have P of 0 and P of 1, I can do P of 2, trace it through my inductive step, use P of 1 and P of 0, and get P of 2. Or if you try P of 1, trace it through your inductive step, and you realize you only needed P of 0, then you only need 1 base case, P of 0, because to get P of 1, I trace through my inductive step, use P of 0 to get P of 1. And then I trace P of 2 through my inductive step to get, I trace P of 2 through my inductive step using P of 1 and P of 0. Does that maybe clarify things? Any other questions? Yeah. Well, I use 0 because the smallest kind of P of something was 0 here. If you had to prove it for, say, n greater than or equal to 5, then you go from 5 to n. Yeah. Yeah.
So I kind of came up with 2 questions. First one was for coming up with the idea of how using is strong induction for this, right? To use the strong induction, our base case, there was like a few points that we should consider if the base case starts from anything other than zero. And like, if not that, then if the truth of P of n plus one does not follow from P of zero, then, or P of n, then we use strong induction. But for this specific proof, base case does start from zero and P of n does imply P of n plus one. So why are we still using strong induction?
Yeah, so P of n implies P of n plus one. So P of n actually doesn't imply P of one. No, P of n doesn't totally imply P of n plus one here. We needed P of n and P of n minus one before you could imply P of n plus one. So if I need more than one proceeding in my inductive step, I strengthen my inductive hypothesis. Right. And also you're asking like, how come in this case the base case started at zero and I needed strong induction? Right. So where the base case starts and whether or not you need so as not to confuse you with the term like strong induction, I want to maybe give you sort of two disjoint considerations that you need to think about. One is that what are the smallest values that I need to prove? The smallest values that I need to prove are, starting at 0, 0, 1, and those are the smallest values I need to prove. That dictates what the base case is. If my smallest values were -1 and 0, my base case would be n equals -1, n equals 0. My smallest values are n 0, n equals 1. My base case, n equals 0, n equals 1. My inductive hypothesis, my sort of quote unquote strong induction, why do I have to strengthen my inductive hypothesis? That is related to what do I need to get to the next one? So how I write this is by considering in my inductive step, what do I need to get to n plus 1? I needed 2 preceding. And that's why instead of using the regular assume P of n, I strengthened this and assume everything up to n. That is disjoint from what my base cases are. My base cases started from 0 because the smallest value I need to prove was 0. In general, I want to give you just for recurrences, this is the kind of cheat sheet background for recurrences. If your recurrence, say like T of n is equal to T of n minus 1 plus T of n minus 2 all the way, let's say, so if this requires 5 preceding terms, 5 base cases, strong induction. Here we have 2 preceding terms, 2 base cases, and your strong induction. Only if there's 1 preceding term, 1 base case, and you can just assume P of n. So if your recurrence relies on 2 preceding terms, 2 base cases, and just give your strong induction hypothesis. So anything more than 1 preceding term, if there are like 10 preceding terms, 10 base cases, strong induction. Yeah.
Let's say this didn't have any preceding terms. What started at like, I know there's a problem there because it's like it starts at 4.
Oh, okay.
Start like 4, 3, 2, 1.
Oh, no. So if it starts at 4, base case starts at 4, nothing below 4. Yeah. Right. So by preceding terms, I mean like a recurrence kind of thing. Yeah. Right. All right. I want to I don't want to run out of time, and so I'm going to erase this so I can cover the functions, kind of the content on functions, and then if there are any questions, you can always post them online, and Tuni can answer them, or you can try to talk after.
No.
All right, I want to make sure to spend the last 32 minutes talking about functions, ways about remembering those definitions and how to do proofs on them. We're almost certainly going to see a problem like this on the exam. If you notice, your practice exam, I think, contains one such question. And so I want to make sure you are able to remember these definitions. So a function, the intuition behind a function is that it is a mapping between two sets. That set, I have a set here, I have a set here, called the set D, the set C. This stands for domain. This stands for the codomain. The way to visualize this function is that I have some elements inside the set called the domain. I have some elements inside the set called the codomain. And the function constitutes the arrows going from elements of D to elements of C. The definition of a function requires very strict requirements on what these arrows must satisfy inside the set D, because very loose requirements for what these arrows must satisfy inside the set C. Before I want to talk about that, I want to tell you about what I want to go into what the definition is and explain to you sort of the technicalities about the domain and the codomain. A function has two important requirements. One is called totality. The intuitive definition of totality is that every single element in D needs to have an arrow pointing out. Needs to have an arrow pointing out of it. Therefore, this diagram does not represent a function because these elements in D do not have arrows pointing out of them. So every element in D has arrow pointing. Second thing is uniqueness, which is that every element in D has one arrow coming out of it. This, let me complete this to make this a function. This now is a function. Every element in D has one, well, or has one arrow coming out of it. I mean, think like, well, how come I specified these two conditions? This is a technicality, so I don't want you to worry too much about this. Technically, totality is that every element in D, there exists an arrow coming out of it, and therefore it could have one or more. Uniqueness is that every element in D has at most one arrow coming out of it, and therefore these two things in combination say that every element in D has exactly one arrow pointing out of it. I think that's what you really want to remember. Every element in D has exactly one arrow pointing out of it. Totality is that there's at least one arrow. Uniqueness is like there's at most one arrow, but don't worry about. But even this, I would take this kind of with a grain of salt. I would think about just functions generally as every element in D. Every element in D has exactly one arrow. This is the definition of a function. A function which maps from D to C has exactly one arrow coming out of every single element in D. This is the notion of a function being well defined. C here is the codomain. The codomain, I like to describe it as the codomain is the set of potential outputs of the function. And I struggle to find the right English word to exactly describe the mathematical construct which is here. C is like the set of all outputs that you like maybe could get. So that differs from the range, which is all outputs that you actually could possibly get. So I like to describe the range as all outputs, all possible outputs of the function. The codomain is all outputs which maybe could be an output of a function. So here, in this case, the codomain is equal to the range because all of these are possible outputs, and all of these are also, say, like maybe, possibly could be outputs. I could also put an element here. This set now also gives me, what could possibly be the outputs, what maybe could be the outputs of my function. It turns out that the only possible outputs are these, and this one is not possible. So therefore, this would be the range. The whole thing would be the codomain. Yeah.
Technically define C as long as like the range is a subset of C.
Right. Exactly. Yeah. So the comment was that any code, like as long as the range is a subset of C, then like C would be a valid codomain. Notice here in my description of a definition of a function, I have placed very strict requirements on how the arrows need to look inside D, but I've placed almost no requirements on what the arrows must look like inside C. Other than that, my arrow, I didn't write this here, but namely that the arrows, can't go outside of C. But other than that, I've placed very, very few restrictions on what happens inside C. The restrictions of what happens inside C are the motivation for the definitions injection, surjection, bijection. What is an injection? I want to give you first the intuitive statement. The intuitive definition of injection is every element in C has at most one arrow pointing to it. What is the definition of surjection? Every element in C has at least one arrow pointing to it. Bijection is just injection and surjection. If you combine these two definitions together, bijection means every element in C has exactly one arrow pointing to it. I want to draw for you, so one more clarification, an injection, every element in C has at most one arrow pointing to it. That means it's 0 or 1 arrows pointing to it. Surjection, every element in C has at least one arrow pointing to it, 1 or more arrows. Bijection, every element in C has exactly one arrow pointing to it, and I think that should be self-explanatory. I want to sort of draw for you an example. I'm going to erase this. So an injection, if I were to give you an example of an injection, something like this. Every element in here has 0 or 1 arrows. Surjection, every element in here has at least 1 arrow. Bijection, everything in here has exactly 1 arrow. One more thing is that injection, surjection, and bijection are only valid when you're talking about functions. If your mapping doesn't even satisfy this requirement for a function, then we don't even start with talking about injection, surjection, or bijection. I want to now give you the formal definition for each of these, or actually for injection and surjection, because bijection is just the and of two. And I want to explain for you why the formal definition matches up with the intuitive idea. Injection, for all D1 and D2 inside the domain, D1 not equal to D2 implies f of d1 not equal to f of d2. Intuitive explanation for here is that any d1 and d2, any d1 and d2 I can find inside my domain, as long as they are different, as long as my d1 and d2 are different, they will map to different values. Why does that work for this definition? Notice here, notice in an injection, what you want to not have is this kind of situation where two elements are pointing to the same thing. And how does this formal definition prevent that? Well, here I have a d1 and d2, which are not the same, but my f of d1 and my f of d2 are the same. And therefore, this violates my definition of an injection. A surjection definition is for all d1, d2, for all C inside C, there exists D inside D such that f of D equals to C. I want to give you the correspondence between the formality and the intuition. Every element inside the codomain, there exists some D, possibly more than one, but there exists some D inside the domain where that value in the domain, where f of D equals C. What do I want to prevent in my surjection? I want to prevent these lonely kind of elements inside C. And how does that definition prevent these? Like, a surjection is basically, I can't have this thing happen. I can't have some like loner here happen. How does that definition prevent it? It's because I'm saying for every element in C, I can always find a D here that will map to it. Why is this not a surjection? Because for this element in C, there is no D that points to it. But my surjection requires everybody inside C has to have some D pointing to it, which doesn't work for here. This is not a surjection. A bijection is simply these two formal definitions ANDed together. Bijection is an injection and a surjection. I want to do an example for you in which I can demonstrate to you how to reason about proofs regarding these, and in particular proofs regarding the composition of functions. Get a new piece of chalk. And so I want to do this problem 7 from my practice questions. Yeah.
Real quick before you do the proof,
Mhm.
Can you draw a graph of a function that is surjective but not injective?
Yes. So the second one here is surjective but not injective.
Yeah, like on a plot, like on a like a function.
Oh, like a graph like this.
Yes.
Okay, so first of all, I need to specify what my codomain is. So if I assume my codomain is the entire real line, something that is surjective but not injective.
Like tangent.
Yeah, so if I graph a tangent, it would look something like this probably.
Yeah.
This is surjective because every point in my codomain is mapped to by some element in the domain, but it's not injective because this point in my codomain is mapped to by many different elements in the domain. Yes. Mhm.
Does the function being surjective mean that the codomain is equal to the range?
Yes. All right. I want to be able to explain this proof. So this proof says, okay, so we have two functions. We have an f1, which runs from set S1 to S2, and a function f2 runs from set S2 to S3. We're given that both of these are bijections, and we want to prove that, let's make sure I get this right, f2 composed f1 is a bijection. When I look at this, one of the considerations that I think of is, first thing, if I want to prove that something is a bijection, that means you have two problems. First one is to prove f2 composed of f1 is an injection. Second proof is to show that f2 composed of f1 is a surjection. Essentially, if you want to prove a bijection, this is one of the most surefire ways to do it. To prove it's first an injection, prove then surjection. Now I want to be able to visualize at least get a little bit of sense of like a visual sense of what's going on here. And so the way I'm going to draw this is I have my S1 here, I have an S2, and my function F1 is mapping these arrows. My function F2 goes from S2 to S3. So my function F2 is mapping these arrows. It's helpful to kind of draw a rough diagram like this so that you can visualize what's going on. Also, what's important, when you're proving something about functions, you always want to figure out what is its domain, what is its codomain. Because especially when you get to compositions, it becomes kind of confusing, what the domain is, what the codomain is. And if you can't reason out what the codomain and the domain are, then the proof will degenerate very quickly. And so here, F2 composed with F1. The way to think about this is I'm doing like F2, let me write this here. I'm doing F2 of F1 of X. And so if I have an input X, what function is it going inside first? It's going inside F1. Then the output of that is going into F2. So when it's written F2 composed with F1, it means I do F1 arrow first, then I do the F2 arrow. So if I write a composition like this, make sure it's important to read it right to left. What is my domain of F2 composed with F1? Well, my input has to be an input to F1 first. Therefore, my input must be a valid input to F1. Therefore, this input has to be in the domain of F1. So F2 composed with F1. So F2 composed with F1 has its domain inside S1. My value X has to be plugged into F1. So my value X is in S1, has to be plugged into F1. I end up in S2, then I take that value, I take this value, which is inside S2, and I plug it into F2, and I end up in S3. So therefore, my codomain is S3. Now that I have worked out what the domain and the codomain of this function are, now I can go about proving injection and surjection. How do I do that? Notice that the definitions of injection and surjection rely on what the domain and the codomain are. And so if I didn't clearly work out what the domain and the codomain of F2 composed with F1 is, I wouldn't even be able to clearly use these definitions. So it's really important that when you have to work this out, you want to be able to work it out with the, you first want to work out what is the domain, what is the codomain, before jumping into the proof. If you have not worked those things clearly, it is very, very unlikely that your proof is going to be correct. Second thing I want, I should have said this at the beginning before doing this problem. This problem is a very, very typical example of a composition of functions kind of proof. Therefore, I encourage you to be able to work this proof out, not by rote memorization, but simply by looking at this problem. Can you just figure everything out? This would be a very, very stereotypical, your very typical example of a composition of functions, your base example. And so if you have a clear understanding of all of the moving parts that are going on in this proof, it will be a very, very good foundation for the exam.
Whenever we're proving injections, either through bijection just by itself, is it in our best interest to use the contrapositive, or is that not always the case?
Yes, I think it's almost always. Whenever I answer sort of these questions, I don't want to give very generalized statements because proofs sort of anything can happen sometimes. But sort of moving to contrapositive is a good idea.
Is that good to hear?
Yes, yes.
Yeah.
All right, so I'm going to prove that F2 composed with F1 is an injection. And what do I want to prove? I want to prove this. So I want to prove. So how I'm going to structure this proof is I'm going to kind of work from the top and the bottom, and I'm going to figure out what are the facts that I know. So what can I use to derive more facts, and where do I want to end up? So where I want to end up is that F2 composed with F1 is an injection. So I write that. So I write the definition at the bottom for all. Let's do D, D1 and D2 inside the domain. What's my domain? It's S1. If D1 is not equal to D2, that implies f of D1 is not equal to f of D2. Or what is my function in question now? It's f of 2 composed of f1. So I can rewrite this as F2 of F1 of D1 equals F2 of F1. Oh, it's not equal to F2 of F1 of D2. Now, as was mentioned, a very, very good thing to do is that if you have this for proving an injection, you just prove the contrapositive. Don't prove this. And the reason for that is slightly in the future, we're going to prove this if statement, and we're going to assume D1 is not equal to D2. When you assume a not statement, you almost have no information because you're assuming that if you assume D1 is not equal to D2, you don't get any information of what D1 like actually is. You just know it's not D2. So you kind of get nothing to work with. You're like basically nothing to work with. And so what's normally very convenient is I'm going to take the contrapositive of this, which means I'm going to move this over before the implies, this after implies, and negate both. So let me do that first. F2 of F1 of D1 equals F2 of F1 of D2, and prove that that implies D1 equals D2. How am I going to prove this statement? I want you to notice that it's a for all statement. And so on the list of tips, and as we previously mentioned in the review session, to prove a for all statement, you take an arbitrary D1 and D2 inside S1. What's the property I want to prove about D1 and D2 is this. So now my goal is that after having chosen my D1 and D2, the property about D1 and D2 that I want to prove is this. Therefore, I want to end up here, F2 of F1 of D1 equals F2 of F1 of D2 implies D1 equals D2. I took an arbitrary D1 and D2, and I want to end up here. Since I took an arbitrary D1 and D2, ended up with this property is true. Because my choice is arbitrary, I can conclude for all D1 and D2 here, this if statement is true. My goal is now here. What is this? This is an if statement. How do I prove an if statement? I assume this. I want to conclude this. Assume this, F2 of F1 of D1 equals F2 of F1 of D2. And what do I want to conclude? I want to conclude D1 is equal to D2. Now I just want to fill in the rest of this proof here. How do I fill this in? Well, let's just think about what kind of facts we haven't yet used. We haven't even used that these two functions individually are bijections. I know that F2 is a bijection. And so I want to rewrite this contrapositive. So I'm just going to write this contrapositive like this. Implies D1 equals D2. Realize F2 individually is a bijection, which means F2 individually is an injection. F2 of this equals F2 of this. Therefore, this is equal to this, since F2 is an injection. So F1 of D1 equals F1 of D2. And the reason for this is that F2 is an injection. Now I'm looking here. That looks a lot like this. F1, also an injection. F1 of this equals to F1 of this. Therefore, D1 is equal to D2. And I concluded that because F1 is an injection. The flow of logic here, I took an arbitrary D1, D2 inside my S. I assumed these two things were equal. Because I knew F2 was an injection, I knew that these individual things were equal. Because F2 of this equals F2 of this, so this is equal to this. I know F1 is an injection, therefore D1 is equal to D2. Therefore, I assumed this and I concluded this. So therefore, this statement implies this statement. I took an arbitrary D1 and D2 inside S1 and concluded that the D1 and D2 satisfied this property. Therefore, for all D1 and D2 inside S1, this property holds. And therefore, this is the definition of an injection. So therefore, F2 composed of F1 is an injection. It's not totally finished because normally I think on a test, you would probably want to write a few more words, like not just write parentheses or something like that. But this is essentially a good map of your entire proof. want to proceed now to a surjection. What do I want to prove? I want to prove this statement. So what's my codomain? My codomain is S3. For all C inside S3, there exists D inside S1 such that my function is f of 2 of f of 1 of D equals C. What kind of statement do I want to prove down here? Well, this is still actually on the outside a for all statement. For all C inside S3, this property holds. So this is a for all statement. How do I prove a for all statement? I take an arbitrary C inside S3. And what's the property I want to prove about the C is this property. There exists D inside S1 where f of 2 of f of 1 of D is equal to C. Now this is my new goal. How do I prove this? How do I get here? Remember at the beginning when we talked about there exist statements, how to prove an existence is to give an example, show that your example works. So first thing here, I need to give an example, or I can give a way to get an example, give a way to get, a D. And then here I need to show that like D actually works. So how do I get this D? How do I find this D? So the method of this is to prove the existence. I have to give a way of generating a D. And then after I give a method of generating this D, I have to prove that the method that I stated to generate this D actually satisfies this property. Because I know that and so why does this prove existence? Like I said, here's if I have my C, I hand you a C, and you say, this is my method to find my D. That's your method. And then here you're saying, my method actually works. If you have a method to find a D, and your method actually works, that means there has to exist this D where this is equal to this. So what's my method for finding a D? And the method helps when you look at this kind of bubble diagram. If I had an arbitrary C inside S3 here, how do I find the corresponding D that points to it? How do I find this D? Well, that's when you think about, well, what have I not used yet? I haven't used that these two are surjections. Since I know F2 is a surjection, I know that there is this, let's call this D2, which is pointing to C via F2. So since F2 is a surjection, there exists this D2 where F2 of D2 equals C. I know F2 is a surjection, so there has to be a D2 which is pointing to C via F2. Now when I have this D2, now how do I find the D? How do I find the actual D? Well, I know F1 is a surjection. So I know that there has to be some D pointing to this D2. That's this D. So since F1 is a surjection, there exists let's say D1 where F1 of D1 is equal to D2. And then how do I get this D? Well, D is just my D1. Set D equals D1. So this is D, so that one's up is D. Now this is just a procedure by which I can find my D. What is my procedure? If I were given an arbitrary C, I'd say, well, F2 is a surjection, so there has to be a D2 which is pointing to it via F2. F1 is a surjection, so there has to be a D1 pointing to this D2 via F1. And so how do I get my D? Well, I just set D equals to this D1 that I found. Now, does this D actually work? Does it actually satisfy F2 of F1 of D equals C? That's my second part of the proof. What's F2 of F1 of D? Well, D is D1. So F2 of F1 of D1. What's F of F1 of D1? It's D2. What's F2 of D2? C. So what is the flow of logic that's going on in this proof? a flow of logic is that I took an arbitrary C inside S3. I took any C, like I told the reader, I said, give me whatever C you want inside S3. So here's my C. I'm gonna tell you a method to generate this D that points to C via, this composite function. How do I find that D? Well, I know F2 is a surjection, so I use the surjectivity of F2 to get me a D2, which points to C. I know F1 is a surjection, so I use the surjectivity of F1 to get me a D1, which points to D2. And then I say, now that I have my D1, I'm going to hand you back my D. It's just equal to D1. Is that D that I handed you actually legit? Like, does it actually work? And how do I prove that? Well, so this second part is proving that D, this way of generating this D that points to my value C actually works. And why does it actually work? Well, I'm going to plug it back into my function F2 of F1. Well, D is D1, so I just replace D with D1. Well, what's F1 of D1? Well, F1 is D1 is precisely the value that's pointing to D2. So F1 of D1 is D2. So F1 D1 is D2. And what's D2? D2 is precisely the value that's pointing to C via F2. F2 of D2 is equal to C. Therefore, there exists this D where F2 of F1 of D is pointing to C. Why do I know it exists? Because I gave you a way to find it. And I showed you that way of finding that D actually gives you a legit D. Therefore, there exists this D where F2 of F1 of D equals C. Now, since I took an arbitrary C and I always found that there exists some D where F2 of F1 of D equals to C. Therefore, for all C in S3, there exists, for all C in S3, this property holds, namely there exists D in S1 where F2 of F1 of D is equal to C. And remember here that because the for all is before that there exists, this value of D can be different for different values of C. Different values of C can have different corresponding values of D. All you need is that each value of C has its own corresponding value of D, but it can differ from C to C. And I think we can see that here. If I use this C, this C has it corresponding to it this D, but this C has corresponding to this D. But any C that I pick always has some corresponding D pointing to it. Having justified these two, having proven this is just a definition. Therefore, F2 of F1 is surjection. And having proven these two, I get that these two are a bijection. All right, so that's basically all I wanted to cover. I'm going to stop the recording. I'm going to stop the recording, and if there are any questions, I'll try to answer as many as I can.